We already had a video on image steganography that explained the technique in a language that you can apply to the programming language of your choice. This is the part where we code it in Python. So if you haven't watched that video, there is a link in the description waiting to get you there. This video will be more about the coding, so stay tuned if you want to see how it's done. Hello Internet, I'm Arya Bagari, and in this video I'll show you how to code the most basic image steganography technique in Python. We will upload videos on multiple more advanced techniques in the future, so subscribe if you don't want to miss those. Once uploaded, all of them will be linked down in the description. We have an image to work with. As you can see, it has a lot of blues and light colors that make it a bit difficult to work with. In general, images that have more chaos in them are easier to hide data in. So now it's time to start installing some packages. We need the Python image processing library called Pillow to get the pixel values out of our original image. I'll also update my pip, cause why not? So we import image from our pill library and then set a variable named img to open our image file. Pretty easy. Now it's time to get all the pixel data out of our image. We can do that with the image.getData. Just to test if it works, I'll print the pixels to my command line. By doing this, we get an idea on how the output on image.getData looks like. As you can see, we have a list that has multiple tuples inside. Each tuple is a pixel, and every pixel obviously has 3 integers inside that are the RGB values. Now we can go over the pixels one by one using a for loop. This is kinda inefficient, and if you decide to make a program out of it, you should use CUDA to utilize the GPU, but we are not gonna go there. Before we do that, we need to write some functions. The first one is to reduce range, mentioned in the previous video. We have to remove some data to make room for our secret data. We named the function reduce pixel range, which gets a pixel as an argument. This function would return a list of 3. If you are new to Python, you might not be familiar with the bitwise operations. So quick lesson. The double greater than symbol removes 1 bit from the data, and the double smaller than symbol adds 1 bit to the data. When put together, these would remove the last bit in a binary number to make the number even. So now our function is done and I can show you how to use it. I'll copy an actual pixel from our image to see if the function works. As you can see here, the function works perfectly, and I've made all these numbers even. Perfect. We will eventually use this function to make our image ready to hold data. Now that that's done, we need another function to encode the data into the individual pixel. This function is pretty easy to understand. It just adds the pixel value and the data together. You could even not make this into a function, but this makes room for more advanced techniques later, and it's generally considered good practice. So we make a new variable that holds our super secret data. It has to have a binary value, so it doesn't matter if it's a Microsoft document or a love letter. You should convert it to binary first. Now we bring back the loop that went over all the pixels. We need to add an enumerate function since we also need the index. I want to show you how it works. But first, I'll add a break since I don't want to flood my command line. As you can see, the I value goes from 0 to 6. I can bring the check up and set it to the data length. So now we are done. I'll add a new list that holds all the encoded pixels. And instead of having a one-time use variable, I just add the encoded pixels to the list in one line. I'm using the red color channel for this. So we are going to feed the encode function with the red values and grab the binary value with the same index from the secret data. As you can see, we managed to perfectly add private data into the red channel. Before we can process the entire image, we need to add padding to our data. We want to be able to separate our data from the junk. So we need to make the data the same exact size as the image. We're going to add a whole bunch of zeros to the end of the data. But we also need to be able to take out the padding that we just added in the decoder. I'll add a 1 as a separator. So in our pad data function, we have the current data and the total size of the image to know how much padding we have to add. Then we use the data length variable to get the length of the current data and add a +1 to account for the separator value. Then we return the current data and a 1. and then many zeros after that. The number of zeros, of course, is the total size minus the data length. To test this function, we are going to run a print statement and see how it works after we set the image size to 20 pixels and feed it the secret data. As you can see, it works like a charm. So now we bring back our loop and make a new variable that holds the padded data. We reduce pixel range in a variable and then encode the red channel and the other two channels without changing them. Now we need a way to save our image, so I'm going to use NumPy. We are going to install it with pip install NumPy, then import it and write a new function called save image to make things easier for us. The save function needs a place to save the new image at, and a list of processed pixels. We also need the size of the original image, so we get the size here, which basically contains the width and height stored in a list. We are going to use the pil image from array function and then the processed pixels with data type set to 8-bit integers, which is the correct data type for pixels. Then we are going to give the array the correct shape by making it take the shape of the original image. The 3 there is for the RGB channels, of course. Then we are going to save the image using the path that we inputted from the user. To make sure it works, I'll call the function with the right arguments, just on the original image, to see if we can make a duplicate. It's gonna take a bit of time, but eventually, we are gonna have a new image that looks exactly like the old one. It has the same dimensions, and the only reason why the size is different is because we switched from JPEG, which is much more efficient compared to PNG. I'm gonna explain why we did that at the end of this video once we are done with the decoder. Now we are gonna bring back the processing code and save the encoded image. Looks almost perfect. Personally, I can't see the difference. When developing Image Steganography code, you should pixel peep to see if there are any artifacts added. There are a lot of weird colors in this image, but they are also visible in the original image, so it's fine. Personally, I can't see anything different. In general, you are looking for colors that seem out of place, and we can't find any. Now let's make the decoder. Same as before, we open the target image and get the pixels. We need to abstract the utils so we can reuse our code. We are gonna store decoded message into a new variable called decoded data. Then, same as before, we are gonna go over the image pixel by pixel, and if the pixel is odd, we are gonna add a 1, and if it's even, we are gonna add a 0. To make it more efficient, we are just gonna add this string of the modulus operations, since it is gonna give us exactly the same thing. We have to, of course, unpad the data here. If I print the decoded data, there's going to be a lot of zeros that we added when we padded the data in the encoder function. So we make a new function called unpad data and give it the current secret data, and use the rfind to find the last one. Remember, this is the same one that we used to separate the padding from the original. So if we slice the data and grab everything before the padding starts, we are going to get the original data. And as you can see, it works flawlessly. Now, if someone runs the same code on the raw image, they're going to see a whole bunch of random zeros and ones that don't really mean anything. We use PNG since it's a lossless format, meaning that it doesn't mess up the pixel values. That's why it has a much larger size. JPEG uses cosine waves to reduce image size, but it also means that the image is not going to be exactly same as before. There is a technique that you can use to hide data in JPEGs that we will discuss in future videos. To show you how JPEG messed up the image, let's run the same encoder and save it in a JPEG container, then see if we can decode it. As you can see, we can't, and we lose our data. So this is it for this video. I hope you enjoyed it. You made it to the end of this video, which means you probably like to know more. If that's the case, like this video, subscribe, and turn on the notification bell so you'll know when the next video in this series hits the web. As always, everything I mentioned above will be linked below the like button. I put many resources like this on my YouTube channel and my personal website, so definitely take advantage of those resources. So until next time, stay paranoid, stay alive.